Okay, so today, girls, what we're going to do is look at polar bonds and polar molecules. And a few key points that you need to know is that a polar bond results due to the unequal sharing electrons. So if we look at, say, carbon dioxide, which has a double bond to each oxygen atom, um, in each covalent bond, there is an unequal sharing of electrons. Now, why does that occur? It's because these two atoms have different electronegativities. If you remember the definition of electronegativity, that was the ability to attract or bond with electrons. So oxygen actually has a greater electronegativity than carbon, so we label that as partially negative. We then label carbon as partially positive. So here is an example of a polar bond because the electrons in the covalent bond are closer to the oxygen than they are to carbon. So we say that this is a polar bond. We can also label the direction of this polar bond, and that goes from a positive to a negative direction, and this is what we call the dipole moment. So the dipole moment is from the positive atom to the negative atom, or the partially positive to the negative or partially negative atom in the polar bond. So in this case, the dipole moment goes from carbon to oxygen to dipole moment. So when we look at carbon and oxygen and carbon dioxide, we label the whole molecule. So oxygen will be partially negative, and we know that carbon will be partially positive. If we then draw the dipole moments for carbon dioxide, we'll have one going this way and one going that way. Now, in a way, just like I suppose a vector, they have a direction and a magnitude. So both these dipole moments will actually be equal in magnitude because they're both between a carbon and an oxygen atom, but they'll actually be in opposite directions. So in a funny way, it's actually the same thing as forces, or when we have any type of vector. These cancel each other out, so we have no net dipole. Basically, that is saying that we have equal sharing on both sides, so there's actually not a positive and a negative end on the molecule. So here we see even carbon being positive, but because it's not a end of the molecule, we say it's non-polar. So carbon dioxide is actually a non-polar molecule. And we can see that, again, because of these arrows cancelling each other out, there is no net dipole. I know in class, girls, my shortcut was to say that we need to look to see if it's symmetrical. And if there was a positive and a negative end. If we see these two things, then we can almost guarantee that the molecule will be polar. So try to look out for those things when determining whether or not the molecule will be polar. So let's do another example. We'll do a trickier example. And we'll do sulfur dioxide. So, first step as always, girls, is drawing our Lewis bond and the shape. So we're going to go SO and then one there, and we actually have a lone pair of electrons there. So this is a bent molecule. If we look at the polar bonds, we have we basically have the same bond. The only difference is a double bond in one, but oxygen is more electronegative, so it's going to be partially negative, and this is going to be partially positive. So we have a net dipole moment going from sulfur to oxygen. So we have polar bonds present in this molecule. We don't know, we haven't decided if it's polar or not, but we know that at least we have polar bonds. So in this case, we look at the net dipoles, and one is going that way and one is going this way. So we have a partially positive end and we have a partially negative end over here. So in this molecule, guys, we do have a overall dipole in the molecule, and that's going from, not sure, it's a different color. That's going from sulfur to oxygen. So we have a net dipole of the positive end going to the negative end in sulfur dioxide. So this molecule is polar. Again, if we go back to these two cheat points, we see that the molecule is not symmetrical, so that's a very good indicator that this molecule is polar. And we see a positive and a negative end. So we see the oxygen being a negative end on both sides, and we have the sulfur being a positive end. So sulfur dioxide, girls, is a polar molecule. Do one more quick example. And that is CCl2, F2. Drawing our arrangement, girls, doesn't matter where we put our chlorine atoms, but we'll have a carbon atom surrounded by 2 chlorine atoms and 2 fluorine atoms in a single bond. So this is actually a tetrahedral structure. Now, it doesn't actually matter what way you put those, because remember it's in 3D, so it actually is always going to be in some this arrangement from one particular angle. So don't worry about where you place those carbon, so the chlorine and fluorine atoms. So again, if we look at these separate bonds, we know that carbon to chlorine is a polar bond because chlorine is more electronegative, so that's going to be partially positive. And then carbon to fluorine will also be polar because fluorine is the most electronegative element and carbon is partially positive. So we have a few strange things going on here because we have carbon being partially positive and we have fluorine being negative, and we also have chlorine acting as a partially negative end. However, this is a difficult one because even though we have negative ends, there is unequal sharing across the whole molecule. So in respect to fluorine, chlorine actually isn't as negative. So there's still a net dipole moment. There's still a pole. It's still overall got an unequal distribution of charge, which is the definition of a polar molecule. So when we actually draw our dipole moments, we do have an arrow going that way because it's going from carbon to chlorine. But because chlorine, the CF bond, the carbon to fluorine is a lot stronger, we can represent that by actually a larger arrow. So if we actually think about this in vectors, that larger dipole is going to cancel out these, so we're going to have an overall dipole in that particular direction. So as we go from this direction to that direction, we're actually going to be positive to negative, which means that this molecule is a polar molecule. Now that one, it would be, I suppose, one of the more difficult ones to explain in a exam or assessment, girls. But if you had to identify it, you can look at this, but again, this molecule is not symmetrical, and because of the difference in electronegativities, there is an unequal sharing amongst the whole molecule. We can say and we can easily identify that this molecule is indeed polar. Alright, hope that helps. Good luck.